It's 11 minutes past 8, as you heard on the news. The World Health Organization has named the new COVID variant, which was first reported in South Africa 3 days ago, a variant of concern. Travel restrictions from Southern Africa have been imposed by various countries. The variant's been named Omicron, and it's now been detected in Belgium and elsewhere. What do we know and how worried should we be? Virologist Dr. Chris Smith is with us. Hi again, Chris.
Good morning, Kim. I'm very well. How are you?
I'm very well. Omicron, what happened to Epsilon and Zeta and so on?
Well, there are other numbers and letters assigned, but they just didn't rise to prominence in the same way that Delta did. So there are some which are gone but not forgotten. They're there in the records, but we've made our way all the way through to that number of variants of concern, which is what the WHO, the World Health Organization, says this is as of today. They're saying it's a variant of concern, which basically means it goes up a notch in terms of how we deal with it, but it doesn't mean it's a foregone conclusion it's going to be a problem. And I'd just like to reassure everybody, at this stage, we don't know very much about this thing other than it's been detected. It's been detected in a number of places. It's been detected spreading a bit, although we don't know the scale of that yet. And it's also showing a number of changes which might, we don't know yet, which might undermine the protective abilities of the vaccine and might confer upon it additional behaviours like greater ability to spread or greater ability to cause serious disease. At the moment, we don't know.
How long will it take us to find out whether our existing vaccines and indeed our antivirals are effective against this?
Well, first of all, you look at the genetic code of the virus, because you don't have to go near a test tube or a petri dish at this stage. You look at the genetic code, and this can tell you a lot, because you can ask, how different is this to the other variants and strains of coronavirus that we've seen hitherto? And that's what first rang alarm bells, because this one has got quite a few changes, genetic changes. Now, all viruses have genetic changes. They're all different in some way. And in many instances, those changes make absolutely no difference to the behaviour of the virus. They're just silent changes. But in this particular one, the Omicron variant, there are about 30 changes which cluster around the spike region of the virus. Now remember, the reason we call these viruses coronaviruses is because they look like a crown, because they have bits sticking out from the surface that resemble a crown. Those are the spikes. That's how the virus gets into our cells and invades us. So if you get changes in that part of the virus, it can change the way the virus gets hold of your cells. It can therefore change the efficiency with which it gets into your cells, which has implications for the infectious dose, which has implications for the infectivity and transmissibility. But the biggest one of all is that we are using the genetic code of parts of the spike in our vaccines to educate the immune system how to recognise and neutralise coronaviruses. So by looking at the code first and foremost, we say, well, look, there are changes there. This will change the shape of the protein a bit. And then scientists will go off, they'll work out how those changes will manifest and how likely it will be, by using computer programs to model this, that the virus could slip past the defences conferred by, say, prior infection or vaccination. And then comes the wet stuff, which is where actually you go and get samples of the virus, we've got those, and you go and get antibodies from the blood of people that have been vaccinated or naturally infected, and you do the simple experiment. You mix the virus, which you know grows happily in the tube in cells normally, with that serum, the watery bit of the blood from people who are immune to the virus, and you see if those antibodies will block the ability of the virus to infect and grow in the cells in the dish, and you see how much actual virus you have to have in there or how much antibody you have to have in there to block that process or accelerate that process. And that tells you how comparable the ability of this virus to grow in the face of an immune response is compared to other strains of coronavirus. And then we'll know what we're dealing with in terms of its ability to bypass immunity. So those experiments are not hard to do. I guarantee that they're underway in laboratories in many places right now.
They would presumably have been going on forever on all the variants, would they?
Yes, I mean, one of the basic things that we're very interested in doing is making sure that we're staying one step ahead with our vaccinology from what the what the virus is doing. And these are simple experiments to do. We've been doing them for decades in virus labs. But what's changed now is our ability to detect these things, because previously we would have had to play with what we were handed on a plate in a diagnostic laboratory. Now, because as soon as we register a positive, we can read the genetic code of those positives, and there's an aspiration to try and read as many of them as possible, because the price of sequencing viruses has dropped through the floor. In fact, reading genetic code is very, very cheap to do these days. So laboratories are aggressively reading the genetic code of key parts of the virus and sharing that data around the world. And what this does is create the virological equivalent of an enormous radar screen. And so you can see blips appearing on your radar, which corresponds to changes in the virus. And the brighter those blips are, the bigger the bulge that they produce on the screen, the bigger the problem. And we can sort of virtually do that now with where these viruses are, how they're moving. We create a sort of antigenic landscape for what the virus is doing and how it's evolving, and you can superimpose on that a sort of ring of fire, which is the protection conferred by the vaccine. And if you see this thing breaching it, you know you're in trouble. It's got the ability to bypass the protective effects of the vaccine. For now, though, we don't know that it can. We don't think that it will.
Chris, we know that there are very low rates of vaccination in Southern Africa. I mean, in South Africa, only 35% of adults have been vaccinated. Is there a causal link between a low rate of vaccination and the emergence of a new variant?
To an extent. I mean, remember that we've got about the same rates of vaccination in a number of European countries where there are ferocious outbreaks surging at the moment, and Germany has got a massive outbreak and about 3/4 of the population have been vaccinated, but there are enough people who are not to fuel quite powerful surges in numbers of the virus. And that's very capable of disclosing new variants of the virus, because you've got people who have been vaccinated rubbing up against people who haven't. And in that way, you're giving a virus a chance to have a look-see and try its hand at what an immune person looks like to try to surmount those defences. So really, the only way to stem this tide of variants is you've got to drive down globally the rate at which the virus is reproducing. But the problem is that all the time you've got people losing their ability to fend it off, which is what happens with time, with waning immunity. You're back to square one. So this is why this is a big headache. We don't produce long-term immunity with vaccines or natural infection to these viruses, so it will keep on boiling up and bubbling up until it basically runs out of room to manoeuvre, which some scientists have speculated, including Sarah Gilbert, who invented the AstraZeneca vaccine. She was sort of making the point at a recent talk at the Royal Society of Medicine that, in fact, the virus is running out of room to manoeuvre, so it's hard to envisage that it's going to be able to change much more, because if it changes much more, it begins to have to sacrifice things in order to stay one step ahead. So it's a bit like if I was confronted with, say, a big wall and I was trying to escape over it and I had a heavy rucksack, I might dump the rucksack to make myself lighter to get over the high wall, but then I haven't got any of the good stuff I had in the rucksack when I'm on the other side of the wall. So you're in difficulty for other reasons. And so these are the sorts of trade-offs that the virus is making as it's evolving to try to stay in step with and continue to spread among the human population.
It's a nice metaphor, Chris, but what would a virus have to ditch in order to become a new variant? What kind of capability would it lose?
Well, in evolutionary terms, if a virus is too nasty, then in fact it's shooting itself in the foot, because it wipes out its hosts and it then finds itself spreading less efficiently, because a virus doesn't have thoughts, feelings and wishes, but we can sort of anthropomorphize it a bit, and we can say what the virus wants is to spread as far and wide and have as many coronaviruses, babies, as possible. It doesn't do that by killing off its host. So over time, viruses and their hosts co-evolve and they make a series of trade-offs so that they become better bedfellows. And this has been happening for millions of years. And a really good example of this, if we look at the herpes viruses, like herpes simplex virus or cytomegalovirus or Epstein-Barr virus, these viruses have evolved to live in the body for the lifetime of the host that they infect. And they come from a time millions of years ago when there were very few populations that were big enough to sustain transmissions of highly infectious diseases like measles. So because you didn't know when you were going to bump into your next victim, they resorted to this mechanism of infecting you for life so that you would ferry them round, carting them about, so that when you did give them the opportunity to spread, they could take that opportunity. And Epstein-Barr virus, otherwise known as the kissing disease, relies on the fact that people do get amorous from time to time when they meet someone that they like. And so what the virus is doing is adapting to not kill you, but keep you alive but infectious for your whole lifetime, so you can keep passing it on. And what do you get in return? Well, scientists have done interesting studies showing that people, possibly, but certainly animals with the animal equivalent of things like Epstein-Barr virus, it does things to the way the immune system works to reinforce certain elements of immunity and give you a more robust response against certain diseases like the Black Death. So if you were to encounter certain pathogens, which would have been very common back in history, because you had a virus on board that changed the way your immune system worked, it tooled up your immune system, fending off the other bad guys to keep its host alive. So in that way, the virus isn't quite so nasty, it's nicer to you, but you're, in return, giving it a home. And that is the way that it tends to work with the evolution of viruses and hosts over time. One becomes less pathogenic, the other becomes more accommodating, and together they form better bedfellows that keep both in circulation.
A few hours ago, the World Health Organization warned countries not to hastily impose travel restrictions. Many countries, of course, have already. But the World Health Organization recommends what it calls a risk-based and scientific approach when implementing travel measures. At what point would one seriously consider closing the border?
Well, Slim Abdul Karim, who I know a bit and is a virologist medic in South Africa, has publicly said today, look, this is a bit of a nonsense, closing all these flights down and things. I mean, it's going to crucify South Africa again because they rely very heavily on international trade and travel because of people going there for the tourism industry, for example. So shutting down borders again is going to spell disaster for that aspect of a country. And he made the point
well,
that
join the club. I mean, it's an assessment of risk, isn't it?
Yes, it is. And he made the point that when Delta emerged, within a very short time, it was in 50 plus countries. So actually shutting the borders to one meant that you were basically cutting off your nose to spite your face because it just comes in from one of the 50 others. And that is exactly what's going to happen here. The fact that we're detecting this and it's already in multiple countries, this bird has already flown the nest. It's a bit like the original story from Wuhan. By the time we knew what was going on in China, it was everywhere. And then, of course, everyone suddenly realised there were fires springing up all around them because the cinders had come down without us realising and started little fires all over the place. It'll be the same. But what governments are doing, by putting in place restrictions early, I think what they're aiming to achieve is to buy time. Everyone accepts,
yeah, exactly.
and our own health minister, Sajid Javid, just said on the news today, instead of the previous language, the messaging was very strong in the past about we're closing the borders, we're keeping out variants. There is an acceptance now that you can't keep this out. You can't keep these viruses from spreading and adapting. We can only slow them down. And the messaging was very much tempered towards that this will buy us time. And what does time do? It enables us to reinforce vaccination because most people are pretty optimistic that the vaccines will continue to work quite well. It's just a question of maintaining high levels of immunity so that really it becomes a case of quantity over quality. If your antibodies aren't so good against a particular variant, you can compensate for that by having a few more of them. So really it's about buying time to reinforce vaccination and learning. So we can do the experiments we were discussing at the beginning of the programme, learn, do the research, understand more about the virus and the threat that it does or doesn't involve, and then you can always reverse your decision to let the thing go. And if it's not looking like it's a major threat, you can do that. What have you lost? Well, a bit of goodwill and a little bit of time. Hopefully, I think we'll know quite soon if this is a major threat or not, and then the government of various countries can make an appropriate decision.
In New Zealand, of course, danger is what always comes over the sea, and people are already trying to build the wall around us once again. I've got a text here saying, we need a quarantine island We need to close all the borders, all air travel from Belgium and Japan and Hong Kong and Israel and the African continent. We could, because we are in a better position than many European countries. Should we?
I think the answer to that question is no, because it is an inevitability that this thing will keep cropping up. It's not going away. If this were the original SARS, then New Zealand's decision, Australia's decision, other countries' decision to draw up the drawbridge, shut the doors and try to sweat it and sit it out, that was a good one. But it's not the original SARS that was short and sweet and easy to spot, easy to stamp out, a fire that was easily extinguished. This is a very different beast. This is not going anywhere. It has endemicized itself, which means it will continue to circulate among all 8 billion people on Earth for the foreseeable future. And the reason it's so good at doing that is because half the people who catch it have no symptoms at all. So unless you are going to have really rigorous screening that's so rigorous that it can find cases that haven't even happened yet, it is an inevitability. You're going to continuously be firefighting forever. So there is a school of thought opening up that what we have to do is to look to history, which is that in the past we had these sorts of incursions of new viruses, including new coronaviruses. There was one called OC43. I diagnosed a kiddie with that today. It's the common cold. But back in the 1890s, it caused a pandemic. It killed a lot of people, very much like COVID has today. But having done that and then gone through the population, it leaves in its wake a population who are immune and better. What we're doing with vaccines in the modern era is fooling the immune system into thinking it's met these sorts of viruses over your lifetime many times so that you have the same risk as you would do were you have caught it all through your life. And that really is going to be the pattern, that we tolerate it, we let it go, we control it by protecting the most vulnerable and building up our own lifelong immunity through catching it from a young age quite naturally and repeatedly catching it every few years actually, and then you end up with a world population for whom it poses no threat, or at least no more threat than the human common cold.
A quick, relatively unrelated question, and you have 60 seconds to answer it. Text says, can you ask Chris why the dose size of the vaccine seems to be the same for big people like me and small people like my wife, given that smaller doses are being considered for children?
Right. The reason for this in 60 seconds is that these vaccines are self-amplifying. They use pieces of genetic code, which when they get into a cell is read and used to make enormous amounts of the product that is written into that genetic code. So actually the dose size doesn't really matter that much. Moderna have reduced the dose of their vaccine for the first booster hit because they realised they could get the same bite and the same pack and same bang for their buck out of half the dose. So that's what they're doing, and it's because what you're doing is growing an immune response. That's not diluted out by body size. That goes to a very discrete population of cells in the body and grows a very discrete population of cells in a self-amplifying signalling way for a short time, and that's why you don't need to vary the dose by body size. So
actually adults could have the same shot as children?
Well, actually, they are giving a slightly smaller dose of the Moderna vaccine to the kiddies. But yes, it doesn't matter if you weigh 200 kilos versus someone who weighs 50 kilos. It's the same, and it will work as equivalently well.
Excellent to talk to you, Chris. Thank you.